Circular functions, let's talk a little bit about them. So circular functions are also one of those things that people find really annoying, and fair enough, they are quite complicated, especially when you're graphing or solving for them. So when we think about circular functions, what we think about is the unit circle. So that beautiful circle which is 1, -1, 1, -1. In a unit circle, the easiest way to think about it is the y-coordinate is the sine and the x-coordinate is the cos. And then the tan is the gradient, so y over x. In methods, we just use radians for angles, okay? Like in 1, 2, you would have used degrees sometimes, but for 3, 4, generally everything is in radians. So if your calculator is still in degrees, I would recommend for you to pop it into radians, and then just be careful about whenever you see questions about angles or anything, just be careful about what they're actually asking and whether they're asking for radians or whether they're asking for degrees in the first place. Alright, so the next thing you need to know is how to remember your exact values. There's 3 different ways. This is the table way. Okay, so table way. So if we look at this is what it's going to be. So this is an angle of 0. This is going to be an angle of pi on 6. This is going to be an angle of pi on 4. It's going to be an angle of pi on 3. And this is going to be an angle of pi on 2. So just remember, those are the key angles you remember. There's 3 different ways. 1, the hand method. 2, table. 3, triangle. This is my preferred method because it's the least memorizey. People do use the hand method as well. Look up a video on YouTube. It's quite beautiful. You basically just like count over the fingers and then count backwards to kind of figure out what's going on. So it's also quite good, but you just need to remember the order of the angles quite specifically. Table is good, especially if you're regurgitating a lot of numbers that you need to use. But I find, so the 2 triangles that for this are the first triangle, which is the 1, 1, root 2 triangle. So that's the pi on 4 triangle. And the other triangle is the 2, 1, root 3 triangle, which is the pi on 3, and this one is pi on 6. And using the triangle, you basically use SOHCAHTOA to find out what each of them are. Cool. Alright, so solving. There is 2 kind of different ways to talk about solving. So the easiest way is to rearrange for a simple equation. So what you're going to try and do is put everything outside of your sine, cos, tan to the other side. So you're going to chuck everything onto the other side. Then what you're going to do is try and find the base angle. So what angle would correspond to the value on the other side? Now, for sine and cos, you want 2 solutions. And why you want 2 solutions is if we consider sine, right? The 2 solutions are located, they're located here and here. And for cos, it's located here and here, right? Because sine, if we think of the one, it's ASTC. So you can do cast for the ones which are positive. Alternatively, you can look at which side's positive, which side's negative, x-axis, y-axis as well. So if we consider sine is positive in those 2, cos is positive in those 2. And we can kind of see like the actual like solutions, they're not evenly spaced from each other. So that means for cos and sine, we need to find 2 solutions per cycle, versus tan, because the positive solutions are here and here, so they're evenly spaced from each other. So that means that we actually don't need to do, that's why our period for tan is only pi rather than 2 pi, because it actually is evenly spaced compared to these 2. So we need to find 2 solutions for sine and cos. Alright, so then you do a quadrant check, which quadrant it is, and you can find 2 solutions for between 0 to 2 pi, and then you just add or plus or minus 2 pi until to fill out the domain, and then you can solve for x. Alternatively, you can kind of skip this step and just solve for x first, and then what you do is you add whatever their period is. So add period. So if their period was 2 pi on 3, you add 2 pi on 3. If their period was pi on 4, you add pi on 4. If their period was 2 pi, you add 2 pi. So let's have a go at doing that. So this needs to be solved over an interval of 0 to 4 pi. Alright, so the first step, we're going to move everything around the sine to the other side. So that's going to be sine x will just equal to a half. Now, a second step is to find the base angle, which means we need to refer back to what we were kind of looking at before, so the triangle. Right. And we identified that we want the 1, 2, root 3 triangle here, so 2, 1, root 3. So that's going to be our pi on 3, and that's going to be our pi on 6. And remember, this triangle is just derived from an equilateral triangle with 2, 2, 2 on each side. Okay, so what we can see here, that's 1 over 2, and we want sine, right? So 1 over 2 would mean it needs to be the opposite of whatever it is. So 1 over 2, that means that it needs to be pi on 6. So our base angle is pi on 6. Alright, let's do our circle next. So in terms of our unit circle, we're going to think it's here and here, right? Because we're thinking these are the areas which their y coordinate is positive, so that's where sine is positive. So the two angles we're going to be thinking of is pi on 6 and pi minus pi on 6, right? So that's x equivalent to that. And we'll have x equivalent to pi on 6 and 5 pi on 6. Okay, cool. Now we need to check for the domain. So those two solutions are in domain, happiness. So if we checked minusing, that would become negative 11 on pi and negative 11 over 6 pi, and that would become negative 7 over 6 pi. So that's outside the domain, so we don't want to go backwards. Now we can check with forwards. So if we go, that's pi on 6, that's 5 pi on 6. Now if we go forwards, that's plusing 12 pi on 6. So we're going to have 13 pi on 6, and the other one is going to be 17 pi on 6. And we can check those, so that would be 24 pi on 6. And that's going to be within domain. Alright, if we tried to add 2 more pi, immediately we can tell that if we added that would be 25 pi on 6. So it's already outside domain. So these are our final solutions. Okay, so those are kind of you might get a question or two of those in exam 1 or on one of your SACs. Importantly, you also might get questions like this where you kind of have compound functions which you need to solve together. And people get really freaked out about these, and kind of fairly so. So what we want to actually do is you want to think back to your polynomial knowledge. Pretend that all of those causes are just a's and you're just factorizing as much as possible, okay? So what you want to do is group like terms, factorize as much as possible, and then treat the causes like x's, and then solve for cos afterwards. And it's going to apply the same way when you have an exponential as well. Sometimes you'll have something like e to the 2x plus, I don't know, 5e to the x minus 3 or something, and you'll freak out and the first time you see it, and then you won't freak out after that, because all you need to do is just sub in a equals e to the x, and then it just turns into a quadratic which you can solve, and then you can kind of revert backwards after. And it's the same for kind of these circular functions. So whenever you see something a bit unfamiliar and it's in exam 1 and you know, oh, I can't use my calculator for this, there's going to be some method where you kind of replace one of the factors to make it more comfortable and to make it something you know better. Cool. Yeah, and never divide out factors, just in general, not just in circular functions, just in general. You will lose solutions. You can always remove solutions after and say, oh, this is why I'm removing it, but you can't just like kick them into space, outer space, and not tell why we're kicking them out into outer space. Okay, so general solutions are a way also to represent circular functions, and there is formulas for general solutions which can be given in like your books and stuff, so you can have a look at those. I personally don't find them like they're good, right? But I didn't use them that much in VCE. I kind of just build it up a different way, and I always found that worked out better because it just made a little bit more sense to me. But you can see which one works better for you, whether you prefer the formula more or you prefer this method more. It's kind of up to you what you want to use. And because of the cyclic nature of the unit circle, we can really get infinite solutions. And that's why we go for general solutions. So if they don't give you a domain, they're asking you to find the general solution. Okay, cool. So it's asking us to find the general solution of cos x equals to tan x. Alrighty, so 2 cos x minus tan x. And why I'm taking it to the other side first is I want to avoid any instance of me just randomly removing solutions. That equals to 1. All right. So the first thing I'm going to do is I'm going to rewrite this tan x as sine x over cos x. Right? And that's going to equal to 1. Now, what I'm going to do after this is I'm going to change this so this is all over the same, like just basically times everything by it. So I'm going to get 2 cos squared x minus sine x equals 2 cos x. Right? Cool. Then once again, what I'm going to do is just move everything to the other side. So 2 cos squared x minus sine x minus cos x. And that now equals to 0. Cool. So then what we can do after this is we can kind of consider like what we want to in terms of the grouping and how we can group the different things together, right? Because now we have our cos x's and we have our sine x's, all of these kind of all together now. So what we can do here is we have our 2 cos x squared. So just like for this previous question here, when we had our 2 sine squared x times cos x minus our cos x, right? What we can do here is we can kind of do something similar where we're going to try and take out the components that we already have, right? And we're going to try and take out like what we can see which is common between the two. So if we kind of move back onto this page, the first thing that we can kind of take out here is going to be our cos x, right? Which is going to revert us back to here. Wait, let me just rub that out. Okay, so what we're going to try and do here is, so we need our 2 cos x equal to be equivalent to our tan x. So let me think of a good way. Oh, wait, yes. So a good way to do this is not to write 1 on the other side. Okay, oopsies, sorry guys. This should just be 0. Because I cannot minus. Apologies for that. Alright, so let me just write in a 0 here. Because when we took tan to the other side, it should equal to 0, shouldn't it? Alright, so when we put that onto the other side, now we can times everything by that. That would still equal to 0. Okay, so now what we can do is, so we've got this cos squared x now is equivalent to kind of this negative sine x, right? So if we kind of consider this as cos x minus our tan x, and we have a look at our kind of unit circle, right? Oopsie. Why won't this work? Oopsie. Okay, I'll just use it on this side. Right away, for what we can actually tell from this one, using our knowledge from talking about minimal domains and stuff like that, is that cos x will not equal to 0, right? So we know that x immediately cannot equal to pi on 2 or 3 pi on 2, or basically, if we talk about in general solutions, it can't equal to 2 pi plus 1 over 2. Yeah. So then we kind of go back to this cos squared x minus our sine squared x equaling to 0, right? And we want to change this so it's something that we can deal with now, right? Because we have this cos squared x and we have this sine squared x, and we kind of figured this out already. So what we're going to do here is we're going to just plug in 1 minus sine squared x minus sine x equaling to 0. Because remember, cos squared x plus sine squared x equals to 1. And that's our Pythag theorem, which is really helpful, right? So if we removed kind of to get cos squared x by itself, kind of change that to the other side. So now what we're going to get here is 2 minus 2 sine squared x minus sine x equaling to 0. And we can do we basically, like I talked about before, we now have this squared part, which is really hard to deal with. So we're going to just change that to a, and instead now we're going to have 2 minus 2a squared minus a, and that equals to 0. Now we can kind of just do a bit of a quadratic type of thing. And what we're going to do here is we're going to say a is now equivalent to 1 plus or minus root 4ac. So b squared minus 4ac, so that's negative 1 squared minus 4a, which is negative 2, c, which is just 2, over 2a, which is negative 4. Right? So we get that. Alright, so then we get a equals to 1 plus or minus, and we can note that that's going to be negative 2 times 2, which is 4. So negative 4 times 4 is going to be negative 16, right? So that's going to just be 16, negative 16. And then what we're going to get here is that it's just going to be equivalent to, so 1 plus that is going to be 1 plus or minus 17 over negative 4, right? Okay, so you can also rewrite this as a squared plus a minus 2 as well if we wanted to. Doesn't really matter either way, I guess. Alright, so then we get to this part, which makes life a little bit trickier, I think, because now we have this fraction. I definitely don't think this is something you probably can solve by hand. So then we can go to our trusty calculators to try and find what it's equivalent to. Algebra solve. And I know it kind of can seem a bit silly to revert to our calculators now, but sometimes we do need to get it into a specific form. And I think that this form was just not something that we could unfortunately do by hand. So let's plug this into our calculators. Just make sure it's on radians. Hopefully my calculator doesn't do the wheel of death, but it did give me a very approximate answer, which is definitely not a good sign. So it gave me that, let's try and just solve this so we can actually find what our thing is first. 2a squared plus a minus 2 equals to 0 for a. So yeah, so essentially it's giving us numbers which are like x equivalent to 0.895 ... and that's in radians, by the way, so however many of that, and then x equals to 2.24 ... So essentially after this step, if this equaled to like a half or something that was easy to do, you would just make it equivalent to sine x, and then you can solve from there. But unfortunately, because it is equivalent, so those are our two base angles, we can convert these to degrees, because it might be easier to work with. Well, it doesn't really matter either way. So the main thing is that we can see here that the period of this is just going to be 2 pi over 1. So it's just going to be 2 pi. So it's going to be whatever this is, plus 2 pi n, plus 2 pi n, because we're just adding the period, so it should be the same. Then we're going to say where n belongs to z. Cool. Awesome. So yeah, that's kind of how it works. If this was a nicer number, we probably could do it fully by hand, but because it was a bit of a gross number, we couldn't really do it by hand for the full process. But once you get to this step, if this, in a question which you can do by hand, you should get a half or something, or like a half, root 3 on 2, 1, root 2 on 2. That's really the only things you can really get.